Hi guys, so in this video we'll have an inquiry section on how a buffer actually resists pH. Here we'll be using a mathematical way of actually visualizing on how a buffer actually works, because in the previous video we have been doing the language way of solving it. So here let's see how now we have two different solutions here, one being a buffer solution and one being just a weak acid solution. So let's try to calculate as a practice, or try to calculate the pH of each respective solution first. So yeah, I will try to solve it, and you can just follow along, or just do it on your own. Pause this video and do it on your own pace and see if your answer is the same as mine. Yeah, without further ado, let me try to solve. So on the left side, we will have a buffer solution that is prepared using a weak acid as well as its salt that contains its conjugate base. So this is actually method 1 of preparing your buffer solution. So as using buffer, the golden formula to use is always pH equals pKa plus log salt over base. Log salt over acid. Using log salt, yeah, log salt over acid. Okay, so here you just punch in the numbers. Okay, it's lagging. Okay. In this case, you can go ahead and calculate the respective concentration, which is 0.1. You have to calculate the mole first and divide by the total volume. But in this case, if you are sharper, so you might realize that the ratio is actually 1:1 right here. So actually log 1 equals to 0, right? Yeah, so at the end of the day, pH equals to pKa, which is simply 4.74. Yeah, so I'll just put it here to remind you all. Log, if they have equal concentration, it will be log 1, which is 0. Let me just check my numbers first. Yeah, 4.74. On the other hand, now we are on the topic of weak acid. So how do we find the pH of weak acid? The long way, or the way to show your working, will be doing the whole ice table. But I know you guys might have your own cheat sheet, those square root of initial concentration times Ka and something like that. I'll just do it the long way. So start off with 1 minus A 1 minus A plus A. So your Ka will simply be A squared over 0.1 minus A. Okay, I'm just speed running this because we've been through this before. So yeah, and yeah, your A, now considering that your A is much smaller than 0.1, I'll put everything here because I have no space. But it will just be square root of so your H plus concentration will be quite a small number. And most importantly, your pH is just a negative log of this would be 2.87. Okay. So with the pH values that we have calculated, please keep the values in mind, because now we're going to find out what happens when we add a little bit of acid to each of the solution. So just to recap, we are now trying to explore how does a buffer solution actually resist pH, and our control setup in this case will just be a weak acid solution that does not have any buffer properties. So on the left will be our buffer solution, while on the right is our control setup, which is not a buffer solution. And let's see what happens when we add a bit of H plus to each of the beakers. So on the left, I think the diagram should be quite familiar by now. So what happens when we add a little bit of H plus? When added into the beaker, on the left, when a little bit of H acid is added, the conjugate base, which is a large reservoir of them, the A minus, will react with the H plus to give you your HA, as such eliminating the H plus. While on the other hand, on the control setup, there's a lack of a conjugate base to react with the H plus, and as such, your H plus can form H3O plus in water, and you get a molecule of H3O plus in the beaker at the end of the day. So now let's go and find out how can we calculate the new pH. Okay, so there's a little bit of mistake here. So here is supposed to be 50 cm cube. So yeah, keep that in mind. So just keep in mind, keep the initial pH in mind. Okay, you know what? Let's just fill up this stage first. So remember, the initial pH just now was 4.74. The other side was 2.87. Okay. So, but now let's go and find out using our buffer equation. How can we use our buffer equation to calculate the new pH? So once again, we need to use the ice table, and we need to calculate a few stuff first. So first, we need to calculate the initial moles of your A minus and HA. So if you recap, initially this buffer solution was prepared by adding 25 cm cube of your salt and 25 cm cube of your weak acid. So let's find out what are their initial pH, which should be the same. So our initial pH should be 25 over 1000 times 0.1, which will be 0.0025. Same goes for this case here, 0.0025. Okay, so I can add these numbers here, 0.0025. So now how about the amount of moles of H plus added? So your number of moles of H plus added will simply be 2 over 1000 times 0.1, which will be a very, very small number, 0.002. Okay, so if you remember, see, when the small amount of acid is added, your base, the light gravity law base will sort of consume it. So consume it by reacting away with it. That's why a small portion of your conjugate base gets reacted away, while your HA and form HA, so that such your HA will add 0.002, and at the end of the day you won't have any acid left in the solution, because that's how the buffering properties of a buffer solution. And now our new values are 0.0027, 0.0023. Okay, we will use this for the there's no enough space now, so we'll continue this on the next slide. Okay, so on the right hand side, what do I have here? We have a weak acid. So, and when weak acid with a certain amount of H plus concentration at the start. So I think if you can scroll to go back a few minutes, the initial pH was 0.00134, and now currently when we add 2 cm cube of strong acid to the solution, the number of moles of H plus in the concentration should rise. So in order to calculate the new pH, all we need to do here is actually calculate the total number of moles of H plus contributed by both the weak acid as well as this newly added small amount of strong acid. Okay, so let's count the initial moles first. Let's use moles. So of H plus would be, okay, it's not very professional to write this. So initial moles of H plus 0.00134 times 50. Originally it was a 50 cm cube of solution. Yeah, 0.00. Okay, then now when we add this, now we calculate the number of moles of H plus. Now that we have added this small amount of strong acid, will just be this plus Right. Now I'm yeah. Okay, so now the new concentration will be 0.00267 divided by 52 cm 52 over 1000, which is 0.00513. Okay, so carrying on to the moving on. So okay, we ignore all this. So now we can calculate. Okay, let's continue on solving the left hand side first. So now that we figure out the moles of the conjugate base as well as the weak acid, the new moles, we can calculate the new pH using the using the buffer solution equation. So pH equals to pKa again. So pKa will just again be negative log of A times power of -5 plus log. So it's log salt over base. So if you want to look back at the previous, so your salt now is 0.0023 and 0.0027. Okay, of course, this is in moles. If you want to convert it into concentration, go ahead. But as I said sometime in the previous videos, all you need to do is to actually just because when you divide the volume by volume, it's the same volume, so you cancel each other out. So there's no point doing that. But now let's calculate what happens. Yeah, the new pH should now be 4.68. Okay, because remember originally the original pH was calculated when this the log salt over acid was 0.0025 and 0.0025, but now there's a slight change in the numbers, and therefore the pH pH changes slightly. So okay, on the right side, now that we have our concentration of H plus figured out, all we need to do is use pH, so it's negative log. I think was 0.00513. Hopefully we get quite a different number here. Prove my point. Okay, yeah, the pH now is 2.29. Okay, so the new pH is 2.29. So now let's compare the difference. For buffer solution, you can see that the initial pH and new pH, the difference when the small amount of acid is added is really very small, which is actually 0.06 only. The pH change was only 0.06 because the buffer solution was able to resist pH change. This proves the point that the buffer solution is able to resist pH change when a small amount of acid was added to it. But on the other hand, for the for the control setup which does not have buffering properties, the pH change was rather significant when only 2 cm cube was added to like a uh, big big solution volume of fluic acid. So therefore, just feel free to go ahead to try this on your own. So instead of a weak acid solution that may confuse you, maybe perhaps you can try just a regular water solution of initial pH 7 and see what happens when you add some amount of acid to it. As because water does not have buffering properties, you can see how steep the pH change could be uh, without a buffering property. So hopefully this inquiry can has let you allow you to visualize mathematically allow you to visualize what does it actually mean when the buffer solution resists pH.